Okay, good morning, Assalamualaikum, and so we'll continue with our lectures. So today we'll move on to a new section of this course. We'll be looking at actions in general. So we will start with actions for the case of things that we are already familiar with. Okay, in this particular case would be the case of classical mechanics. Okay, I think you have come across this idea of action, hopefully, in classical mechanics. And if you have not, then no, I will just go through briefly, and essentially you should be able to see the connection with the Lagrangian mechanics and Hamiltonian mechanics. So let me begin with the idea of particles. If you want to solve the classical mechanics problem, you usually would like to have the idea of position of the particle being solved from Newtonian equations of motion. So the idea is again adopted here. So in other words, what we do want to solve is essentially the following. Get my you can see this. So the idea is essentially to think of your particle having positions. So the position is actually this will be running from I equals to 1 to 3 here. Okay, I'm using the same notation that you have probably have seen. Your QI here is what we call the generalized coordinate. By the way, can somebody confirm that you have done this before? Anyone? And this Lagrangian mechanics?
Classical mechanics.
Okay, great. So, so this generalized coordinate will depend on time, for which you need to solve this from some equation of motion. Okay, but usually, if you think of what your Newtonian equation of motion is essentially just this. Okay, so this is a second order differential equation. So in other words, if you want to completely solve this, you need to do integration twice. Okay, so in other words, having just your coordinates only will not be sufficient to actually completely solve your Newtonian equation of motion. Okay, so you need to supplement this with essentially what we call generalized velocities. So you have qi dot being simply just your time derivative of your qi. Okay, so your action of your particle will be the integral of the Lagrangian. Okay, the Lagrangian will have, say, the in this particular case, I'm generalizing this to n particles. Well, okay, n variables. Okay, I might absorb this idea of particles inside together with the degrees of freedom. So you have this q1 to qn to be your degrees of freedom. And then along with that will be your velocities corresponding to the degrees of freedom. Okay, and you also allow your Lagrangian to be dependent on time in general. Okay, but we will no. I think in this particular case we probably concentrate more the one which is not explicitly time dependent. But never mind. The idea of an action essentially is this. So you integrate this Lagrangian function with respect to time over certain interval. Okay. So if you have not seen the Lagrangian before, I hope everyone does. No, the Lagrangian is normally given in terms of the kinetic energy. Okay, so this is kinetic energy, and then this is potential energy. So somehow this quantity of the difference between the two sort of gives you the Lagrangian function. In the old literature, this is something like a kind of measure that tells you how the system can do work. Okay, so but I will not go into those archaic kind of notation. Okay, so essentially the Lagrangian over here will determine this action. Okay, and what we need to do is to think of this all this qi and qi dot, okay, can be varied, meaning this might not be just a specific path. Okay, so this, let me just mention this so one can talk about having your QIs giving you a path, like just one book. Okay, giving you a path, but the path can be varied. Okay, so the idea is if you vary all the possible paths that you can have inside this Lagrangian, there'll be one that sort of minimize your action. Okay, so this is essentially the thing that one does in variational calculus. I think that is also have been treated at least in, I think, mathematical physics, I think, probably, and then also classical mechanics. It depends on how you teach it. So you can jump straight into Lagrangian mechanics without action. This is no, which is unfortunate, really. The principle of least action is one of the most important principle of physics. Okay? Even the high energy physics in particle physics will actually simply use principle of least action. Okay? So we apply this saying that, okay, there will be one path sort of minimize the action, and that is the one being truly realized by the particle in the classical mechanics. Okay, so all right, so let's see how we can actually do this variation. So the first thing that we need to do is we need to fix the path between a certain interval. So here is interval between t1 and t2. So there will be one extremum path that sort of gives you this. Okay, this is given by this solid line, and the other one will be the variation, which is shown in terms of what we call the dotted lines. So these are variations. Okay, and we need to be able to do this variation in such a way that at the endpoints they are essentially fixed. Okay, and in between it can do anything. Okay, so that's the main idea. Okay, so you introduce the variations to this path, which you have yet to solve this. Okay, by allowing your path given by your coordinates here to depend on some free parameter. Okay, so here you have a free parameter sort of parameterize the variation of the path. Okay, so your parameter can go from some interval here given by minus epsilon to plus epsilon. Okay, and as I said, we need to fix the endpoints. So that means at the endpoints where you take t equals to t1 and t equals to t2, it always gives you the same point. Okay. So and the other thing that we assume in this particular case is the fact that for the remember that it depends on lambda. Okay, lambda is a variation of the path. The path is supposed to sort of solve the variational calculus, the stationary of your action. Okay, so we assume this is going to be true when you take your action to be uh, evaluated at lambda equals 0. So at lambda equals 0 essentially gives you the extremum path. Okay. So what one do now is essentially, since now there is a free parameter parameterizing the path, so your action itself will be a function of this parameter. Okay. So what one does is the fact that when you differential of this action, which can be given in terms of the derivative of your action with respect to the parameter lambda, and then you take the lambda to be equals to 0, that should give you the extremum path. Okay, lead to extremum path. Okay, so let's try to do this. So you have this Lagrangian inside your action. Okay, remember the action is the integral of your Lagrangian with respect to time over this interval. Okay, and now what we need is to take the derivative with respect to this parameter that we have introduced. So we can take essentially it's like a chain rule in some sense. Okay, we do a derivative of your Lagrangian. Okay, Lagrangian depends on q, and your q depends on lambda. Okay, so in other words, if you take the derivative of this, you have to do a kind of a chain rule with respect to its Lagrangian function. So you have derivative of your Lagrangian with respect to the q, and then the variation of your variation of your q itself, which is really your derivative of your q with respect to lambda. Okay, and then the other set of variables that we have over here are your generalized velocities. Okay, so you take the derivative of your Lagrangian with respect to the velocities, and then your velocities with respect to your parameter. Okay, and over here we think of this as the same as the time derivative of your variation of your path given over here. Okay, so we plug those things in, and if you do that, you'll see that here depends on two different variations. One is delta q, the other is delta q dot. Now it would be much more simpler if all these things will be dependent on just delta q. But you can actually see that this can be done because this is just d dt of delta q. If we can get rid of this d dt, then no, everything will be dependent on this delta q. And how do you get rid of this is to do integration by parts. Okay, so the integration by parts that you need is to take the total derivative of these two factors over here. So you get d dt partial L partial q dot delta qi, which is actually later on when we take the time derivative, it will give you the delta qi dot. Okay, but let's consider this now. Okay, you have this total time derivative, and then you take away the time derivative of partial L partial qi dot. That will give you partial L partial qi dot, and then the time derivative of delta q, okay, which give you the delta qi dot. Okay, so I hope you understand the logic behind this. So it's just integration by parts. Okay, so next, can we simplify this further? Yes, you can. Essentially, you have a total time derivative over here, this particular term. Or the other thing that we need to remember, that you have a summation over all this I. Okay, so here I make it general in the sense that I runs from 1 to n. Okay, because you might consider particle will have three degrees of freedom, and then you consider say m particles, then you will have 3m particles, which we write as n. Okay, so it's just the number of degrees of freedom. That's the most important thing. Okay, so this total time derivative integrated over time will just give you this integral. Okay, I hope you understand this. Okay, I mean, this is just evaluating this integral, but you have a total time derivative. Essentially, you just evaluate this function at the endpoints t2 and t1. But at the endpoints, you have actually seen that before. You get that delta qi at t1 equals 0, and delta qi at t2 equals 0, because we fix the condition there. Okay, so you get the second term that we get over here will just go to 0. Now there is a more general way to think about this. You can even have a non-zero contribution, but that just make the things slightly more complicated. But in the end, you get some idea of an extremum path. Okay. So we'll just set it to be equal to 0. So now what's left from the integral above? This goes to 0. Okay. So you're left with this and this multiplied by this common term delta qi. Okay, so you can bring out delta qi at the back, and then you have this thing sort of multiplying the variation here. Okay, and then this will be integrated over time, but remember, we are actually getting this from your variation of your action, and we require that this variation of action should be equal to 0 for the case where lambda equals 0. Okay, so now once we do that, okay, the only way that this can be equals to 0, because delta qi is arbitrary. Okay, the only way you can have this is to make this thing in bracket to be equal to 0. And this is essentially what is known as Euler-Lagrange equation that you probably have seen in Lagrangian mechanics. Okay. Now, what precisely this Euler-Lagrange equation seems to tell you? Let's do just a simple example, one free particle. Okay, so one free particle here, you just have three degrees of freedom. Okay, so your kinetic energy here is just the sum of your kinetic terms with respect to the 3 degrees of freedom. Okay, and then your potential here, I'll leave it general over here as any function of q. And then if you do this, then you'll see that when you take the derivative of L with respect to q, that will just give you remember that here is something that depends on q dot, and here is something that depends on q. So the only term that comes that has explicit q, remember this is a partial derivative, the one that depends on explicit q is your potential. Okay, so in other words, the L dq over here will just give you minus dv dq. Okay, and then we have the other one, which is essentially inside a time derivative here. So you have partial L partial qi dot, and over here the term in the Lagrangian that depends on qi dot is just coming from your kinetic energy, and when you differentiate this, you get mqi dot, which is essentially your momentum. Okay, so what one puts all these things, okay, put inside this Euler-Lagrange equation or there, then what you have is essentially the following equation, which says what? Which says that the rate of change of your momenta is equals to your this is equals to your potential. Sorry, I'm just lost for you the word. The rate of change of potential with respect to the position. Okay, and this we recognize as your Newton's equation. I think there's some problem with the minus sign somehow. Let me just figure out. Okay, that's fine. What you get is you get a double negative sign inside here. So you have a minus sign outside here, and then L over here is T minus V. Okay, T minus V. So you get a minus. Essentially, if I just substitute that, really what do I get? I have mqi dot, maybe I'll do this step by step. I will have partial L partial Q, which gives you minus dv dq. I'm going to ignore the indices at this stage. And then I have minus d dt m qi, okay, now my mqi dot. That will have to be equal to 0. Let's see if I can make this mistake go away. So I would really need a minus sign. That's the thing. So that you bring on this to the other side. So I have pi dot equals to minus dv. Okay, so there's a mistake there. Okay, right. So now this is probably you have seen this in the context of Lagrangian mechanic. In Lagrangian mechanic, probably you would not write this way. You will probably write it in terms of mq double I dot equals to minus dv dq. Okay. So this remember in Lagrangian mechanics you have not really defined your momenta as yet, but your momenta gets defined when you do this definition. Okay, and once you do this, you define this new variable instead of qi dot. You have this pi instead. Okay, and if you want to use this as a variable, you go to what we call the Hamiltonian mechanics. Okay, so the Hamiltonian mechanics is given by making this transformation. You probably have seen this before in probably if I taught you statistical mechanics, this is what we call the Legendre transform. Okay, so you do a Legendre transform changing from your Lagrangian to the Hamiltonian. Okay, so the Hamiltonian, just for simplicity's sake, is just equals to t plus v compared to L equals to t minus v. So your Hamiltonian is now a function of what? It's a function of P and Q. Okay. So if you take the variation of your Hamiltonian, you'll get the following. You get so you have dpi here. Okay. You vary your p's, so you get dpi here multiplied by qi dot, and then by right, since this is a product of two factors, I should be getting pi dqi dot, okay, which we'll treat in a minute. And then the other one is coming from here is partial L partial qi dqi, okay, but you also need to have your qi dot, so you have partial L partial qi dot dqi dot, and you can see now this is actually your pi, and that will cancel off your dqi dot, which is precisely what you get when you do Legendre transform. Remember, in Lagrangian, you have your variables to be this, okay? But you exchange your one of the set of the variables to this, okay? So that's why this gets crossed out, because you are really doing change of the dependent variables, okay? So you get finally you get the following, okay? So you get dpqi dpi dot and partial L qi dqi, okay? But what's the h? If I treat it as a function of q and p here, then this would just give you partial h partial q dqi plus partial h partial p dpi, okay? And then you start to compare between these two different expressions. Then what do you get? You get qi dot, okay, qi dot dpi. That means dh dpi equals to qi dot, okay? And then the other one would be this one, partial L partial qi with a minus sign dqi. You compare with this, then essentially that tells us, okay, the partial h partial qi is negative of partial L partial qi. And this two set thing, by the way, yeah, this is essentially, let me just think, partial h partial qi, I should be getting a pi dot. Where does that come from? Oh, yeah, sorry. So this is partial L partial qi, but remember we have the following in your Euler-Lagrange equation. Okay, so in other words, this, which appears over here, will be equals to this, okay, which is essentially your pi dot. Okay, oh, it's already written down here. Okay, so this two set, which is what? qi dot partial h partial pi, and then the other one is pi dot equals to partial h, sorry, minus pi dot equals to minus partial h partial qi. So this is called the Hamilton's equation. And this replaces your Euler-Lagrange equation. So the benefit of Hamiltonian mechanics is what happens over here. If you look over here, let me forgotten the dot there, it's supposed to be there. Okay, over here is actually a second order differential equation with respect to time. So you have a first time derivative here and then another time derivative over here. So it's a second order dE. Okay. dE. Over here, this equation gets converted to this Hamilton's equation, which is really a first order dE, but the number of equations now increase. Let's say these are n equations, n second order dE. Over here will be 2n first order dE. So in terms of the number of equations with respect to the degree of the derivative is actually the same. Okay, but you know that first order dE are much easier to solve compared to second order dE. So that's the reason why this in some sense is much more better compared to the Lagrangian case. Okay, right. So now these are the thing that we have discussed here essentially is supposed to be something that you have seen before, okay, in your classical mechanics or variational calculus. So now the point to do this is for the case of relativistic particle. Okay, as we have seen earlier that your action is actually is an integral of your Lagrangian over time. But if you do in this particular form, okay, it will be dependent on your reference frame coordinates. So it's not desirable to do that in this particular context. Then it will depend on your action will depend on your frames. So we need to convert this to an expression that sort of independent of frames. And one can actually do this by considering instead of the integral over your coordinate time. Okay, so this is coordinate time. Convert it to the case of your what do you call this? This is called the proper time. And proper time, you remember, is an Lorentz invariant. Because the way we define it, it depends on, I can't remember the precise expression, but the tau is related to your ds squared. Okay, if you remember. Okay, so in other words, by changing this, will answer partly how to express your relativistic formalism into how to change your action into some partially into a relativistic form. Okay, is there somebody to check? Right. So and then we recall what it is the tau. The tau is precisely this relativistic factor. Actually, it's 1 over gamma here. Gamma is 1 on square root 1 minus v squared on c squared. Okay, and this, if you look at this, this was just transformed back to the one using the time coordinate. So in other words, no, this is fine. Okay, but the point over here, using the proper time, it really is a Lorentz scalar. Okay, and this Lorentz scalar is independent of whichever frame that you actually use. Okay, so but that's, as I said, it's only half the story. The other half of the story is the integrand. Okay, the integrand over here is L gamma. So we require L gamma to be also a Lorentz scalar. So then what happens is you multiply this to be a Lorentz scalar, and this is already Lorentz scalar, then the whole action will be a Lorentz scalar. Okay. So how can we actually do this? So in order to make this as a Lorentz scalar, then you can only allow your path to depend on your velocity of the particle in a trivial manner. Okay, so an easy way to do this is just to say that your L gamma is going to be constant over here. Okay, and this should be able to work. And then if you look at what will be your expression for your Lagrangian here, will be your constant, whatever this constant is supposed to be at the moment. Okay, will be your Lagrangian will be equal to that constant that we have picked up somehow. Okay, multiplied by your factor of 1 over gamma, which is now becomes square root of 1 minus v squared on c squared. And if you remember that this is the full relativistic expression over here, you can actually expand this as a Taylor series, provided that v is much smaller than c, so you can use your Taylor series of your square root. So you get 1 minus half on v squared on c squared over here. And you can see that, okay, this looks familiar. Okay, if I choose the right constant over here, then this could be turned into your kinetic energy, which is precisely the terms that we have for the classical case. Okay, so the constant that we need to put in, okay, the constant that we need to put in over here will be your rest mass energy. Okay, so what's your Lagrangian then? Your Lagrangian then will be this constant. I think we need to put a minus sign here because to get rid of this minus sign over here. Okay, so you get minus mc squared multiplied by this inverse of your relativistic factor, which is 1 minus v squared on c squared. Okay, so that is how we sort of come to the point of defining your relativistic Lagrangian. Okay, and this, as I said, if you have your v on c to be less than 1, okay, then you can expand this and then you get back your kinetic energy. Okay, but let's look at what is your momenta in this case. Okay, your momenta, remember, is defined as dl dqi dot. Okay, so it's dl dv. So you need to differentiate this Lagrangian here with respect to v, and v only appears inside this relativistic factor over here. So you need to differentiate a square root. So that gives you 1 over square root over here with a half. Okay, and then you differentiate the thing inside, that gives you minus 2v on c squared multiplied by the constant that we had outside here, which is minus mc squared. This 2 minus sign will actually cancel off. Okay, and then you get c squared multiplying this 1 over c squared over here will just give you mv. The 2 also will cancel off. Okay, And this is nice because this is essentially your earlier relativistic what you call form of your three momenta. Okay, so this is great. This is something already is something familiar. Okay, and let's see what the Euler-Lagrange equation is supposed to be. The Euler-Lagrange equation seems to give you what? Well, the first thing is remember that you have your partial L partial Qi dot, sorry, partial L partial Qi. That is partial L partial X over here, where your X is supposed to give you the coordinates of the particle. Okay, but if you look at this Lagrangian, there is no X. So that gives you a 0, and you're left with minus d dt partial L partial V, which we already calculated, and that is essentially telling you that you have your relativistic momenta over here. So d dt of relativistic momenta will be equal to 0, and that gives you essentially the conservation of relativistic momenta. Okay. Now, that is in terms of Lagrangian mechanics. We could turn it into Hamiltonian mechanics. Okay, there are a few things that I can think of to say over here. One of the things in relativity, it sort of okay. Earlier I mentioned about the second order differential equation in Lagrangian, and then your Hamiltonian mechanics will actually give you, instead of second order, you give yours first order. So in that sense, your Hamiltonian formulation is actually preferable. But in the context of relativity, one snag that comes about in the Hamiltonian formulation is that you need to be able to define your coordinate time, because remember you have this idea of dqi dot to be equal to pi. So we need to take the coordinate time derivative. Okay, so in that sense, you are dealing with something which is dependent on reference frame, so which is not so good. Now you can also see what's happening over here. If I do remember the Legendre transform going from Lagrangian to the Hamiltonian, okay, I will have now, I'm just doing this in this form over here because I know this is going to be your relativistic energy, okay. So what's PRQI dot? That's P dot V, and then your L will be just L. So what's P dot V? Your P essentially is a relativistic momenta over here. So you just dot with that V, okay. So you get mv squared, which is really related to your relativistic kinetic energy, okay. And then minus L. Okay, remember your L is essentially minus mc squared, square root of 1 minus v squared on c squared. So your minus and then your minus over here will give you a plus. Okay, and then you see that I'm going to add these two things up. Okay, but let's see what this is. So maybe I just give you the steps. So if I were to make this to be, maybe it's not necessary, okay. So I have mv squared over the square root. So let me just write that thing. So yeah, okay, never mind. So I have m is a common factor for both, so I can bring it outside. And then I'm going to bring outside this square root. Okay, So this will just be your V squared okay, let me just write that down first, and then again your m is a common factor there, so that will be plus c squared, and I'm bringing out this square root at the denominator. Okay, so I would really how can I bring out a square root at the denominator? I would just multiply with the square root here divided by the square root, right? So now that square root is a common factor, so I bring it outside over here. So this will be now 1 minus v squared c squared, and you can see there your c squared cancels out with this, okay, and then what's left is your minus v squared, which cancels out with this. So you're left with essentially this expression, which you already know that this is really your relativistic energy. So your Hamiltonian is really your relativistic energy. But as I said, this requires us to define what P, which depends on your time coordinate. So in other words, it's not so relativity friendly. Okay. Right. Okay. The other thing is one can re-express this in terms of your P squared and your rest mass energy here. So you get your epsilon squared equals to that. Okay, this is from your earlier relationship between relativistic energy with your momenta here. So your Hamiltonian now becomes this. Okay. So that sort of gives you what you call the Hamiltonian for the case of a free relativistic free particle. Okay, so there is no your particle is actually moving freely. Okay, but you have this modification coming from the relativistic factors. So let's think the next thing that we wanted to do is essentially the charged particle case in an electromagnetic field. But let me pause at this stage to see if there are any questions. Anyone? No? Okay, let me take a few minutes break, maybe around 3 minutes. Okay. Okay, everyone's back. Okay, so let me continue. So again, our point is actually to sort of make the small step transition going from just particles to particles with other things. In this particular case would be your electromagnetic field. So let's try to do this in terms of your Lagrangian thing. So in the ordinary context of Newtonian mechanics, okay, so essentially this would be given by your kinetic energy again, okay, T minus V, okay, this is your kinetic energy, And what happens in the case of your potential energy will be corresponding to your electromagnetic field, now written in terms of your electrostatic potential, your scalar potential. Okay, so we need to somehow generalize this later on when it goes to involve your magnetic field as well. Okay, so how do we do this? Remember, your electrostatic potential or your scalar potential is only a part of your four-dimensional potential, your forward potential earlier. Okay. So your A mu, for example, over here is given by your vector potential here, and then your scalar potential. Okay. Vector potential and scalar potential. Okay. So somehow this Lagrangian that we have for the case of Newtonian mechanics will have to be replaced using this four-vector potential. Okay. So okay, this is just getting your covariant case. So your covariant case is just the same thing, but your fourth component is replaced by a minus sign due to this minus sign over here. Okay. So what else do we need in this particular case is the fact that, okay, if you look at this, okay, this part is somehow connected to our earlier Lagrangian, okay, which is the one which says that I have minus mc squared times the square root. Okay, that will give you that half mc squared. But this one again will need to be replaced by something which is Lorentz scalar. Okay, and your gauge potential over here is not a Lorentz scalar, it's a four vector. Okay, so what we need is to make the contraction of this four vector with another four vector, and the what you call the natural candidate will be your velocity. Now this is the reason why we had earlier we mentioned that your Lorentz scalar, okay, your Lorentz scalar will be allowed to depend somehow also on velocity, because we need this for this particular example. Okay, so here what we can do if we say that, okay, I'm going to do this Lorentz scalar thing, okay, which is given by this expression over here. You just contract the components over here. So this will have A dot V minus phi C. And if we look at this particular form, okay, then remember I need an E phi here. So when I do this, I have a phi C instead. Okay, so that tells us, okay, I really need this E on C multiplying A mu, V mu, so that I will be able to get your minus phi C, the one for the Newtonian case. Okay, so let's assume that we do have this instead. Okay, so the Lagrangian now will be a new Lagrangian. Okay, given by the old one. Okay, multiplying your 1 over gamma thing, and then the other Lorentz scalar will come from here. Okay, so this will give you that. Okay, the new Lagrangian for charged particle in electromagnetic field. Okay, now let's see what are the new things that's involved in this particular Lagrangian. If we take this to be a Lagrangian for the case of the particle in electromagnetic field. So what are the new things that we're going to get? The new things that we're going to get is your canonical momenta, which is defined as partial L partial V. Earlier, there's only that term coming in, but now you have also this V coming here. So essentially, this is capital P, okay? Just to differentiate the normal small p. Capital P here is given by mv over the square root, the mv times gamma, really. Okay, and then you have plus E on CA. And if you look at this, why is this a plus? Getting problems with the minus sign over here. Right. So that's your relativistic momenta here. So let me check on this. Okay, I will check later on. Okay, but what I need in this particular case is essentially okay. I know this is the right answer. So that's why I'm a bit puzzled about this, and that naturally comes from that. But never mind. I'll check this later. But essentially, your canonical momenta, the conjugate momenta that you had earlier, is going to be replaced by this new thing. Okay, so your momenta of the particle gets what you call, it gets modified by this factor, which comes from the electromagnetic field. Okay. Now, does this make sense or not? Well, we can go to the case where you have your conjugate momenta as an expression inside your Hamiltonian. So let's see whether this works or not. Okay. So remember your Hamiltonian is given by PI dot minus L. So this will give you P, the capital P dot V minus L. So P dot V gives you the three-dimensional, the old momenta here, your P, the small p here, P dot V, and then you have this modification factor here given by that. Now it becomes a plus. I'm getting trouble with this. Somehow my plus and minus sign is everywhere. Okay, I'll check this later, but somehow this will cancel off that. Okay, and I'm left with this E phi plus the MC squared. Okay, and this one combines with that to give you the relativistic energy. Okay, and then essentially I will have the other part will coming from the electrostatic potential, which is precisely what we know earlier. Okay, but now if I really want to get an expression for the Hamiltonian in terms of this new conjugate momenta, I will need to use this again. Okay, and then this will be written in terms of the new conjugate momenta, capital P, and then you sort of re-invert this to get your expression for your H. Okay. So this will be your Hamiltonian for the case of charged particle in electromagnetic field. So I'm just worried about the minus sign. Let me just go back here. That's minus E5. That should be plus. Okay, I have to check this later on. I can do this at this moment. Okay, now let's now write this Lagrangian in terms of this. Okay, so you have minus mc squared 1 over gamma, which is your square root thing, and then your part that interacts with the electromagnetic field, okay, with this four-dimensional velocity here. Okay, if I really okay, your four-dimensional velocity here with respect to the proper time. If I were to write this in a much more elegant way, let me just check what I'm trying to do here. I need to go back to the case of your field strength tensor. Right. Right. So let's just write this thing out first. So 1 over gamma squared is 1 minus v squared on c squared. And this can be written in terms of your contraction between your metric tensor with your velocities. Okay. So this will actually define as your velocities, one of them as a contravariant vector, the other one will be a covariant vector. Okay, just think of your metric tensor here is sort of what do you call this, as lowering your index. Okay, and your h dot mu will just give you v squared minus c squared, and then that will actually checks out with this thing over here. Okay, right. Now what we want to do with this is to be able to use your velocities written in this way, so one can actually do the Euler-Lagrange equation in terms of your four-dimensional vector. Okay, so let's see whether this actually works. So let's do the derivative with respect to the four vector here. So you get for this one, remember previously it was 0 because you just have L equals to mc squared square root 1 minus v squared earlier. Okay, but now, as I said, because due to the interacting term with the electromagnetic field, you have dl dx mu to be given by this term over here. Okay, where a nu comma mu is essentially your partial a nu divided with respect to partial x mu. Okay. That should follow from this Lagrangian that we had. Okay. So remember what we are doing here. We are taking the derivative of partial the derivative of L with respect to S mu. Okay, the whole thing. So we get that for one of these terms over here, and then we have to do the other one, which is with respect to the velocities. And with respect to the velocities, we will have this term coming in, and also coming from your a mu here is already having that h dot mu. Okay, so that will just give you a mu. Okay, So we need to find out what this is, and this is the reason that we have done above, is that to write this as, if you look at this, this will be 1 over c squared x dot mu x dot mu. Okay, so this is that. This is the same as that. Okay. So now, how do you differentiate this? So remember, here is actually a function here, a square root. So you take the derivative with respect to the square root first. So you get 1 over square root, and then you have a factor of a half. Okay, and then you differentiate what's inside. So there are two x dot here. One is x dot nu on top, x dot nu at the bottom. One could really treat them as follow. Let me try to see. So remember that, okay, let me just write this thing down first so that you can see what's happening. Dx dot nu dx dot mu gives you delta nu mu. Okay, which means if mu and nu is not the same, okay, in terms of their components, it will be 0. If it's the same, it equals to 1. But this, remember that we are only so far differentiating that. You should also differentiate that. Okay, but I can really rewrite this. Okay? I can rewrite this as s dot mu x dot mu. So in other words, this product will give you twice this this kind of term. Okay, and remember here you need to. Okay, let me do this. I hope it's clear, but just a bit upset about the earlier minus sign, I suppose. So I need to have d dx dot mu of x dot mu x dot mu. Okay, so one of them. So if you differentiate that, I will get x dot nu with delta mu nu. Okay, and then I do the reverse. I will also get x dot nu delta mu. Okay, so you get twice of that. So that's what you have over here. Okay, and you have this factor as well. Remember, I'm putting this as rho instead of the nu, because if I do nu, then I'll have too many nus multiplying in a single term. Okay, so I just have to replace the dummy variable. So what is this? This is just this term. Okay, this one will get replaced by mu, so I have x dot mu there, and then I have a c squared over here, so c squared over here, and then finally, if you multiply everything out, you get this one. But essentially, this will actually give you the four velocities v mu. Okay. So in other words, your dl partial L partial x dot mu will give you this, inclusive of this earlier one, which we have left out to just concentrate on that. Okay, so we get this. Putting this inside your Euler-Lagrange equations, okay, then we have this thing will be time differentiated, so you get that. Okay. And when you do a time differentiation, then you have to do a time derivative. So one could actually try to do again a chain rule. Okay, so the chain rule will sort of give you this one goes to the other side. Okay, this one goes to the other side. And then this one, when you take time derivative, so you know that your a mu here is a function of your axis. Okay, so you need to do a chain rule kind of thing, so you get that. Okay, so finally you multiply with your gamma. You multiply with your gamma, this will turn into the proper time. Okay, and this will, your x dot mu here, x dot mu here will change to your four-dimensional velocity vector. Okay, but what do we have here? It's a nu comma mu minus a mu comma nu. That is precisely your field strength answer. So your Euler-Lagrange equation gives you something which is essentially something that we have seen before, which is the Lorentz force equation. Okay, and your Lorentz force equation in this particular form will go back to your earlier version of your vector potential and your scalar potential. Right. So finally, one could reduce this equation, okay, by evaluating the each component to this equation, okay, which is the thing that we have recognized as your Lorentz force equation. But we also have the fourth component, which actually gives you this. Okay, and that you can actually see that this is your energy, relativistic energy here. Okay, the time derivative, and that corresponds to this one. Okay, you just follow the step. I'm going to skip some of this thing. I think that's all I want to say at this stage. Yeah. So in other words, what we have over here, we have done everything in terms of relativistic form. Okay, your Lagrangian, we have your Lagrangian earlier. Okay, now written in terms of the relativistic form is given in terms of this. Okay, and then not only that, if you use this as a Lagrangian that depends on your four-dimensional vector and your four-dimensional velocities, okay, then yeah, I think that's right. Yeah. So this is your, with respect to the coordinate time. I probably have said something else. Okay. This is your coordinate time. So that's why you need to have that factor gamma. But okay, the only thing that we are worried about is the minus sign earlier. So once you do this Euler-Lagrange equation, okay, then you get back to your Lorentz force equation in the relativistic form. Okay, and that translates to the Lorentz force equation, the familiar Lorentz force equation. Okay, so I probably want to stop sometime here, I think, because that let me get back to that minus sign problem earlier in the next lecture. What else I want to say here? Okay, the one that we have done so far are just thinking of a particle. The one that's of concern is the particle, and your electromagnetic field is actually just having the It's just the role of the electromagnetic field is just like an external field. Okay, so here when I say external in this particular case, it's just like thinking of it as a field which is put by hand, and that field is not having any dynamics. Okay, so in order to address this, so that means over here no dynamics involved. So when you have no dynamics involved, there will be no, I mean, it's like an incomplete kind of problem. So one has to introduce dynamics to the electromagnetic field itself, and that requires us to introduce the idea of variational principle for electromagnetic fields. So we will do that. I think it's best to do this in a different lecture. So I will stop earlier today. Is that okay? So let me take the attendance here. Okay, that's done. So are there any questions before we stop? The notes I have already uploaded it, so I have to find out what that minus sign, and then I will tell you in the next class. Okay. Any questions? Immediate questions before we stop? I guess no. Okay.
Not yet, doctor.
Okay. So I'll stop now. So I'll see you next week, inshallah. Okay. Okay. Bye, everyone.
Thank you, doctor.
Bye.